Hey, Erin.
Hello. Okay. Do you want to go ahead and share your screen already? And I'm sure everyone will start joining again.
Yeah. 1 second. I cannot put my camera on, right? Is that
You should be able to put your camera on.
says you cannot start your video because the host has stopped it or something.
Okay. Okay, I guess when there we go.
All right, now it works.
Okay, and you should be able to share now as well.
Okay. So this one.
Good. So welcome back, everybody who should be joining now. We'll go ahead and get right into the second masterclass. I hope that you were able to use the coffee break a little bit. And I know it's takes some getting used to maybe with the different system. Yeah, we'll have another coffee break after this masterclass and pitch sessions, and then there'll be breakouts. So I will go ahead and give over to Toni.
All right. Thank you, Erin. Can you see my screen and can you hear me?
Yeah, we see you and we hear you. Thank you.
Okay, perfect. Yeah, good afternoon, everyone, and thank you for joining this masterclass. And what I want to talk about is sort of one step higher in length scale to what Tom discussed like an hour ago. So Tom discussed the fundamentals of electrocatalysis and how to control electrocatalytic materials. And now we're going to try to go one step further into more of the chemical engineering and transport phenomena space. Before I start, I wanted to give an overview of our group. It's a young group at Eindhoven where we are interested in electrochemical technologies, namely electrolyzers, fuel cells, flow batteries, everything that has to do with electrochemistry and flow. We are primarily interested, and we use material science, and particularly we like to control the microstructures, so thinking about three-dimensional structures, pore sizes, distributions of pores. We're also interested in coatings and particularly in modifying wettability, as you will see today. And we are also very interested in characterization methods such as neutron imaging and X-ray tomography to try to look at electrochemical phenomena that happens during operation in electrochemical reactors. And I will show you a couple of examples of each in this lecture. So like I said, Tom introduced very nicely the fundamentals of electrocatalysis and the need to develop electrocatalytic materials that are active, selective, and durable. And from there to actually putting those materials in a big electrochemical cell, there is quite a big gap. And that space, that gap is what we're trying to fill by contributing to your catalytic layer engineering, thinking about how do we control the three-dimensional structure of an electrode. So think about gas diffusion electrodes. How do we control your mass transfer phenomena, particularly multi-phase mass transfer phenomena? So that is a problem on a length scale where chemical engineers we feel very comfortable. And our goal is really to develop these guiding principles that would allow us to fabricate and characterize porous materials for next generation electrochemical systems. And this is the polarization curve, is the typical footprint of an electrochemical reactor. And Tom was particularly discussing the kinetic overpotential. So theoretically, we would have a thermodynamic voltage here called open circuit voltage, but we know that in reality, as our current increases, the cell will experience certain inefficiencies or losses. And in electrochemistry, we like to group them up into three categories. The first one being activation over potential, that's related to electrochemical kinetics. So thinking about surface area, about activity. The second one is related to ohmic. So that really has to do with ionic conductivities in your electrochemical cell and also electronic conductivities, thinking about contact resistances, electronic conductivities in solids. And last but not least, mass transfer overpotentials. Those become very relevant when we move to operations at very high current densities. And there, the porous electrode plays a crucial role because it should be able to still distribute fluids, reactants, at the same time that is removing products. So there is a lot of interest to develop these three-dimensional electrodes and coatings to control mass transport. And really the vision is this one. You're all familiar with it, so I will not spend time and integrating renewables through large-scale energy storage, electrochemical conversions, and then of course use in transportation sectors. And today I want to tell you three very short stories of how we can engineer porous electrodes, porous materials to enhance the performance of electrochemical systems. And I will first start by talking about an example of low temperature fuel cells. And the reason why I picked this is because I think a lot of the science and engineering that has been developed for fuel cells is actually much more mature than the science that is being developing in CO2 electrolysis. And I think there are a lot of interesting ideas that can be repurposed from fuel cell technology into CO2 electrolysis. I will tell you a very brief story of our recent efforts on CO2 reduction, particularly on thinking about how to make gas diffusion electrodes. And last, I'll tell you a brief story about how to control 3D porous structures for Redox flow batteries. Okay, so let's start with the first story. And before I start, I wanted to remind you how a polymer electrolyte fuel cell works. In the anode, we have hydrogen gas. In the cathode, we have oxygen from the air. And we produce water, electricity, and heat. Now, the problem is that on the cathode, at high currents, you produce a lot of water. And this water has to leave the cell at the same time as the gases are coming into the catalytic area. So that is what we call mass transfer limitations. And it's a very relevant problem, a very important problem in fuel cells called water management, but also in electrolysis, if you think about bubble management. And if we think about CO2 electrolysis, if we want to generate, for example, organic products, I suspect that this will also become a problem in the near future, particularly if you want to go to high currents. So on the cathode, what we have is typically a membrane, then a catalytic layer here, and then we have these gas diffusion layers or gas diffusion electrodes that I'm sure you're all familiar with, which are composed typically of carbon fibers and then a hydrophobic coating, typically PTFE, Teflon, yeah? And the reason why you put in a hydrophobic coating is that the water or the products can come out as quickly as possible. Now we know from experiments and theory that the water at the micrometer scale will follow these tortuous paths, which are determined by the material microstructure and the local surface chemistry. Now, in chemical engineering language, this is what we call decrease effective diffusivity, because the gases are forced to travel longer distances, increase tortuosity, right? So how can we rethink this problem to try to channel the water and the gases in a way that they follow straightforward pathways at a micrometer scale? And that is really what we've been thinking about for some time is, can we change the local wettability of these gas diffusion layers or gas diffusion electrodes to force the liquid product, in this case water, to travel through these straightforward pathways. And as a consequence, the remaining areas will stay dry for the transport of gases, okay? So this is a fundamental problem. The fundamental challenge is really controlling multi-phase flows at a local scale. And how to do that, that's challenging because it requires modifications of contact angles and wettability through thick materials. And this is the only equation I will use today, which is the driving force for a liquid product when there is a gas counterflow, the capillary pressure, that can be calculated as 2 times the surface tension multiplied by the contact angle, and the contact angle tells you something about the wettability. So contact angle is higher than 90 is hydrophobic. Contact angles lower than 90, that is hydrophilic. And it also depends on the pore radius. So as we will logically expect, the water is going to preferentially fill the pores that are hydrophilic and that have large radius, okay? Because the pressure, capillary pressure is lower. All right, so we were determined to essentially modify the contact angle, and how do we do that? So we begin with a carbon fiber substrate that is a conductive scaffold. I'm sure that you're familiar with these carbon fiber substrates. And first, we coat it with hydrophobic polymer like Teflon. And you expose that to a thermal treatment so that you can evaporate the solvent and sinter the polymer. Now, this is traditional state-of-the-art hydrophobic GDEs. And the new step is that we expose these materials to an electron beam using masks that have a predefined pattern so that the radiation can go through some slits. And next to that, we immerse this material in a solution of hydrophilic monomers. And that way you end up having a material that has a structured hydrophilic and hydrophobic domains through the entire thickness of the material. And that's why we use electrons, because they have the ability to go through the entire thickness. Now, for those of you who have played with GDEs, you know that they are very hydrophobic. The water doesn't want to stay on the surface, it rolls off. And you can see how these materials look like. You can essentially wick in the water through these patterns. All right, so very briefly about the chemistry, we used a envinyl formamide, which is a monomer that polymerizes after electron radiation. This happens at low temperature, 70 degrees. And after a very short time, only 10 minutes, you have already decreased your contact angle that was initially 100 degrees all the way down to about 20. So you turn a very hydrophobic surface into a very hydrophilic surface. And then we looked at how the patterns look like. So remember that we irradiate from the top, and then there are these masks. And this gray area here is the GDE. And we essentially did the EDX analysis to visualize the local composition of the different elements, such as carbon, fluorine, and chlorine from the grafted molecule. And we can see that there is a good fidelity between the top and the bottom interfaces. So we have a proof that there is some sort of chemical pattern, that there is some chemical modification on the surface. But we wanted to see how the transport characteristic looks like. And for that, we perform a capillary pressure experiment. So this is a microfluidic cell in which we pump water through a channel. And we control the capillary pressure precisely and visualize using neutron radiography where the water is located as a function of the pressure. That allows you to build these graphs of water saturation as a function of position that ultimately allow us to calculate this saturation as a function of capillary pressure plots. And this is a lot repurposed from the field of oil and gas, right? So thinking about displacement of fluids in a solid, in a porous material. And what you learn from these curves is essentially that at a very low capillary pressure, the water will fill the hydrophilic regions. And then at a much larger pressure, the water will fill also the hydrophobic region. So the space, the separation between these two lines will tell you something about the quality of this pattern, the segregation of this pattern. But the interesting thing is when you then take this material and you predict, so here we used pore network simulations, so three-dimensional simulations, to calculate the increase in effective diffusivity, because we do this work to increase to decrease the tortuosity, and as a consequence to increase the effective diffusivity. And what you can see in these simulations is that when you compare an unpatterned material, so a baseline with a pattern, GDE, you can see that you gain at a saturation of 0.2 or so, you gain about double effective diffusivity, and that translates in electrochemical performance. So it does make physical sense to go from unstructured wettability materials to materials with pattern wettability. And modeling, so three-dimensional modeling, can help you inform the development of materials. But the final effort was, of course, to put these samples into a fuel cell and measure the electrochemical performance. So like I said before, polarization curves at different conditions. And what we see is that comparing the blue, which is the modified material, with the red, we were able to see that the mass transfer overpotential is lower in the case of materials with pattern wettability. And so we attributed these improvements in performance due to a better water management. And we did a lot of Neutron work to learn where the water was going in operando. And this is what I'm trying to explain here. I thought this technique might be interesting also for some of you looking at electrolysis. And the idea of neutrons is the following. So with X-rays, we are all familiar. An X-ray will tell you essentially where the bones are, and the water is nearly transparent. So it attenuates very little. With neutrons, is quite the opposite. So if you have a robot, so if you have a metallic structure, neutrons will go through heavy elements without attenuation, and it will give you signal about the water that is underneath. And this is, of course, just a sort of a joke representation, but the idea is that every electrochemical cell is composed of metals and carbons and polymers, and that is all nearly transparent for the neutron beam. And what you can see inside is to look at lighter materials such as water, lithium, boron, and that's why neutron radiography is a very powerful technique to look at, for example, multi-phase transport. Okay, and that's what I do here. I look at the fuel cell during operation, and I can differentiate and see water locations under the ribs and under the channels. So it allows us to do a local quantification of the water distribution. And we couple that with in situ performance. So we build that in the beam line. You can put your fuel cell and you can look at it and you can quantify. So it's not only a qualitative, but you can quantify local water compositions or saturations in the porous media as a function of the operating condition. And here I'm showing you an example at 2 amps per square centimeter, where we compare a baseline material in black with a material that has pattern wettability in red. And you can see that the water preferentially locates on these hydrophilic patterns that we created before. So the interesting thing here that we learn is that the total amount of water is about the same. So it's not that by making hydrophilic patterns, you get less water in your porous media. You get about the same total amount of water, but what changes is actually the distribution of this water. And if you have a 30% of the area fully saturated, but 70% nearly empty, that would already give you a fundamental advantage in terms of mass transport. Okay, and yeah, another exercise where you can use neutrons, and the reason why I put this here is because I realized that the work on CO2 electrolysis is going in this direction, which is beginning to use microporous layers, changing temperature as well. So here you can see the water distribution at 70 degrees and with a microporous layer. Here is when we remove the microporous layer, we can see that the water segregation gets even more clearer. And when we go to lower temperature, you can see more condensation. And as a consequence, there is even a more clear segmentation between hydrophilic and hydrophobic. Okay, and with that, I conclude my story about fuel cells. And hopefully, while fuel cells and CO2 electrolyzers are different, hopefully that can stimulate some ideas on how you can tackle the design of gas diffusion electrodes. With that, I want to move briefly, this would be just 2 minutes on a gas-fed CO2 electrolyzers, which is, I presume, the interest of many of you in the audience. And I think you all understand the motivation of moving from flat planar electrodes in thick liquid electrolytes to gas-fed CO2 reduction, as that allows you to have thinner diffusion layers, and also not being limited by solubility limits on the liquid electrolyte. And what we are basically doing in the field now is repurposing a lot of the knowledge that has been developed for fuel cells. So a lot of the GDE concepts that are used now based on carbon fibers and microporous layers were driven from fuel cells. But there are several unique challenges, I believe, for CO2 electrolyzers that motivate the development of radically new material concepts. And one of these problems relates to, again, multi-phase transport, and particularly, and I'm recalling to the same equation that I used before, the capillary pressure that determines the transport of liquids when there are liquids and gases. Depends on the contact angle and the pore radius. But all this material development was performed for water, right? Because fuel cells and electrolyzers, they basically ran with water. But now when you move to CO2 electrolyzers, and particularly if you are interested in producing organic products, so think about formic acid, methanol, ethanol, propanol, all these materials have much lower surface tension than water. And as a consequence, the contact angle and the capillary pressure characteristic will change. And here we basically, we wrote a paper a few months ago where we tried to highlight that problem, which is, what is your operational envelope that allows you to produce a certain product without flooding a gas diffusion electrode, at least a current generation gas diffusion electrode. And you can see that your window is pretty narrow, particularly when you move to these higher carbon atom alcohols like propanol, where with very tiny amounts, very tiny concentrations of propanol in water, you would already break through and flood your gas diffusion electrode. So that makes us think, how should we be designing gas diffusion electrodes for this particular system? And I think that is going to require new concepts for controlling the 3D microstructure of the material, but also, frankly, for controlling the the surface tension, new coating chemistries, new coating concepts, and so on. And I have a final 5 minutes. Erin, do I still have 5 minutes?
Yes, go ahead.
Yeah, okay. Excellent. I will go very brief through that, but I thought that some of the microstructural work that we're doing in flow batteries could also be interesting for CO2 electrolyzers. And in a flow battery, it's nothing else than an electrochemical reactor, like a fuel cell or an electrolyzer. The only difference is that now the tanks are reversibly charged and discharged. And essentially, there are several components. One of them is the liquid electrolytes or liquid dissolving tanks. And then you have your electrochemical reactor that looks a lot like a fuel cell or an electrolyzer, with your membrane in the middle, with your flow fields or fluid dynamic elements, and finally with your porous electrodes in between. And so we have been thinking now for a long time about how to design porous electrodes, and particularly how to control this complicated mass transfer problem, which is you have to provide diffusion, convection, migration, and also electrochemical reactions within this 3D structure. So there is a lot of interesting science to be discovered there. And then, of course, if you're an electrocatalysis person, there are a lot of interesting problems as well happening at the interface. So very briefly, what we are interested in is how does the 3D structure of the material influence its performance? And we have looked at different non-woven materials, and we have also looked at a woven material, so material that is like a fabric, like a textile, really. And we've used model platforms to try to deconvolute what is the role of mass transfer. So we want to know the mass transfer overpotential as a function of the material type, okay? And by doing that, we realized something really interesting, is that all these non-woven electrodes, they kind of collapse through the same trend line that give you moderate current density, and they take quite a lot of pressure drop to pump the liquid through. However, when you move to these woven, these are very well-organized materials with aligned channels, with large pores and small pores, so bimodal pore size distribution, you get the best of both worlds. So you get very high current densities at the fixed overpotential, and you also get low pressure drop. So we got very interested in these materials, and we collaborated with the University of Surrey to try to understand, using three-dimensional modeling, what are the reasons why these materials actually work so well. And one of the things that you learn from the modeling is that if you have a material that has, like, for example, this SGL paper, that has a poorly defined microstructure, that might be beneficial perhaps for fuel cells or electrolysis. But in this particular application, what we see is that the material performs worse than this cloth in a flow battery. And the reason we believe is that you have these big pathways here that give you high electrolyte flow velocity. and then these stagnant areas over here where there is essentially 100% conversion. So your electrochemical reactor is actually underutilized, right? You have big areas of the reactor that are not producing any current, and some small areas that are producing all the current. And that is a situation that is suboptimal from a mass transfer point of view. When you go to very aligned pores, hierarchical structures, then you get the best of both concepts. So anyway, the last very thing that I have is that we are now developing our own scaffold, so our own 3D structures for use in flow batteries, but also for use in CO2 electrolyzers, for use in fuel cells. So we want to control from the bottom up the microstructure, and we want to be able to make structures that have either isoporous pore size distribution or porosity gradients, or bimodal or trimodal pore size distribution. And what we use is a technique that was developed for membrane materials, actually. So non-solvent induced phase separation is a very facile method in which you have a polymer solution, you cast it on a mold or on a glass plate, and then you immerse it in water to create the separation of the two phases. Ultimately, you get with a porous membrane or a porous scaffold that you carbonize at high temperature to produce the conductive electrode. And by changing a few parameters, a few easy parameters, we were able to produce isoporous structures that have a porosity gradient, and structures that have these big pores, these microvoids. And we think these are desirable properties for electrochemical systems based on the theory that has been developed in the field. So we just tested this material that resembles like a sort of like a honeycomb, because it has these big pores through plane, and then it has these small pores in between. We tested these materials in flow batteries recently, and we were able to see, this is particularly for an iron chemistry, that the performance goes up by a lot. So the overpotentials are reduced, and there is a lot of work on optimizing the surface chemistry that needs to be done, but the starting point is already very interesting. So if some of you have ideas on how these materials could be integrated in CO2 electrolyzers as well, I would be happy to hear and potentially to discuss collaborative efforts. And with that, I conclude my talk. Thank you so much for your attention. I hopefully convince you that engineering porous materials can unlock next generation electrochemical systems. And I gave you an example of controlling local wettability. So how changing the contact angle allows you to have higher mass transport. I told you another example of thinking about flooding and material durability. And a final example of controlling the three-dimensional structure to improve flow battery performance. Thank you all for your attention.
Great, thank you very much, Toni. I think we have a few minutes for questions, so why don't we get right to that? And the first one that came in, it says, in gas-fed electrolyzers, how can we enhance the stability of membranes for long-term operation?
Are you talking about membranes as in polymer membranes, or you're talking about these gas diffusion electrodes?
Yeah, it doesn't say in the question.
Okay. Oh, because you're reading, I get it, yeah.
Yeah, sorry.
So maybe if that person can clarify, what I can say for now is that I haven't focused myself on membrane development, so really on polymer membrane development. There is a lot of good work happening in the Netherlands on that topic. I focused on trying to maximize durability from the point of view of the gas diffusion electrode. And to answer from that point of view, I think you want to have a material that allows you to have a stable operation without flooding for thousands of hours, even if you go to high current densities. And the hows to do that, I think you should think about pore size modifications, even local pore size modifications. So perhaps you need to have smaller pore sizes closer to the areas that they can flood, and bigger pore sizes closer to the areas that you want to have high diffusivity. I also think that we need to think about coatings much more, about surface chemistry treatments. So everything is now done with PTFE, and that's great. But I think there is room for more exploratory science there.
Great, thank you. I think maybe one or two more. Could you please explain why woven carbon fiber is better than non-woven?
Yeah, Yeah, we do think that the fact of having a bimodal pore size distribution, so if you think about a cloth or woven material, you have two families of pores. You have the big pores that happen at the intersection between threads, right? Those are about 100 microns. And then we have a lot of smaller pores that appear within one specific bundle of fibers. So in one bundle, you have 100 fibers approximately, and the distance between fibers is about 8 micrometers or so. So in chemical engineering, we know that if you want to enable convection, for example, you need to have larger pores. And if you want to enable diffusion, then you need to have smaller pores. So I think the combination of both the large and the small pores is the key advantage as compared to non-woven materials.
Okay, great. Let's do one more. Says, I would like to know how accurate is it possible to calculate the current density in woven electrodes? I
want to know how accurate is it possible?
I guess how accurate can you calculate the current density?
Yeah, so I don't know exactly what you refer to, so perhaps you can clarify. But if you're talking about experimentally, well, we measure the total current, and we typically divide it by the geometric area. We also measure indirectly the electrochemically active surface area by doing double layer capacitance measurements. So that's our experimental way to determine. If you're talking about theoretically, that is harder. In that particular work, we use tomographic microscopy to reconstruct the images and geometrically calculate what the surface area is. But that has a downside, which is the minimum resolution of the machine is about 0.3 microns or so. So there would always be a under prediction of the surface area because of that.
Okay, great. Thank you very much. I think that's all the time we have. Toni, if you see the Q&A, you can maybe answer. I think there's one more question in there. So feel free to do so. And for the rest, after the pitch presentations that we'll do now, there will be a coffee break. If you go to the community tab on your app, then to meetups and virtual meets, you'll see a part that you can click on. And if you scroll down, you'll see the opportunity to have a bit more discussion with Toni for the coffee breaks before the breakout sessions start. So great, we're gonna go on now to the project pitches, but thank you very much, Toni.
Thank
for
you.
your presentation.
Thanks.
Good. Then I would like to invite Marilia to go ahead and present.
Okay. Can anyone hear me? Erin, can you hear me?
Yes, I hear and I see your screen. Thank you.
Okay, well, good afternoon, everyone. My name is Marilia Popo. I'll be introducing the part of the project that actually deals with electrolyte for optimizations for the electrochemical reduction of CO2. A little bit about us. My name is Marilia Popo. I'm working under supervision of Professor Ruud Kortlever and Professor Wiebe de Jong. We're actually located at TU Delft. We're inside the Department of Process and Energy, and we're also part of the e-refinery initiative. Our group is named the Kortlever Group. We have a website. If you Google Kortlever Group, you end up having dealing back to the website. We're focused in 4 major areas. That would be dispatch electrochemistry and mechanistic studies, development of novel electrocatalytic materials, process conditions and optimization, upscaling and device engineering towards electrochemistry. For this project, we're focusing on electrolytes, and electrolytes have the potential to actually influence the electrochemical reactions. And they actually control the system according to variations in pH. They can improve selectivity, and most importantly, they can actually influence the CO2 concentration in the system. So for the E2C solution, we're proposing a mixture of acetonitrile, water, and ionic liquids. The goal here is to tailor the proportion of proton donors in the system and the availability of CO2 in the system as well by improving its dissolution. Ideally, we're aiming to reach an optimized electrolyte, which would have the perfect proportion between proton donor and CO2 dissolution in the system. When I'm dealing with results, I'd like to show you a little bit how the research is actually done. So we're using a flow cell. This flow cell is this sandwich structure that it contains a working electrode, a counter electrode, and a membrane separating the cathode and the anode chambers. The entire system is actually linked into, I can actually use a laser here. It's linked into a GC. So while we're actually running the experiments, we're doing online reading of the gas products, and we have a constant flow of CO2 coming into the system, which tends to keep the CO2 concentration in the system stable. As I said, the system is hooked up to the GC, which leads us to an online gas chromatography analysis. And after the reaction is actually finished, we carry out a sampling of the liquid products and run it through HPLC. So if I want to see the results, what I'll be looking at is, of course, a chronoamperometry, which is basically the experiment where you determine a potential, you apply it for a certain amount of time, and you carry out the analysis of the products you obtained. So these products that we go through periodic efficiencies calculation, and we estimate in percentage how much of the electrons that we produced during a reaction was actually used to produce one product or another. In this specific graph that you are seeing, you have two lines, a black and a red one. The black one is the standard benchmark electrolyte that's used. So if you look in literature, most of the literature for CO2 reduction is working on 0.1 molar bicarbonate, sometimes a little bit more concentrated, sometimes a little less. And we have in red the electrolyte that we are actually proposing. One of the mixtures that we're proposing, we're still looking into the research, but we already see an increase in the current densities. So this is an advantage to the system. Increasing current densities means there's more electron available, means that in molarity, the products will be produced in the higher rate. But we also reached these results. So on the top graph, you have the first set of potentials that were analyzed using bicarbonate as an electrolyte. And on the bottom graph, you have the second set of potentials that were analyzed using, in this case, acetylnitrile and a 5% concentration of water. You notice that we lost the black bar, which is referring to hydrogen. Of course, we had less water in the system, the proton donor were less, so we lost that bar. But we also increased the formation of formate and acetic acid. This kind of result is what we're aiming to actually obtain progressively, dealing to the optimized electrolyte that we're proposing. So the potential for the impact of this research is that industrial application of electrochemical reactions, they're mostly being hindered by matters of selectivities, current densities, and all of these can be addressed through proposing different kind of electrolytes, which can actually promote selectivity and can also increase the dissolution of CO2. The team here is working in close collaboration with VITO, TNO, and Antwerp. So we're doing the electrolyte analysis, but the other institutions are actually working on development of the cells and also the catalysts. And the major takeaway of this research, of our end of the research, is that the electrolytes actually have a very large role in influencing the CO2 performance. And when you have the mixtures, in this case a ternary mixture, they have a good candidate that could actually improve this production. And at the end, we can lead to an industrially viable system if we actually tune the electrolytes to optimize it in an easy and low-cost manner. So if you'd like to discuss more on this topic, please join our breakout session. It will be carried out between 4:20 and 4:50. And thank you for having us here.
Great, thank you very much. Let's hand it over to Yuvraj from VITO.
Yes, can you hear me?
Yes, we do.
Will you share the screens?
Yes.
Erin?
Yes.
Okay.
Okay, go ahead.
Good afternoon, everyone. My name is Juraj Bierja. I'm from the Flemish Institute for Technological Research, VITO. If you go to the next slide, VITO is a research institute working on sustainable technology. We work on in 5 different domains: health, energy, chemistry, materials, and land use. We are from the electrochemistry team, which is within the chemistry department. And our ambition is to develop new techno-economic feasible processes for Power-to-X and CCU applications, and for the electrification of the chemical industry, supporting the low carbon energy transitions. So we have projects about CO2 reduction, nitrogen reduction, biomass conversion, hydrogen technologies, and main focus is working towards demonstrators and pilots. So in this E2C project, we are mainly involved in the catalyst integration and the development of gas diffusion electrodes. Next slide. So the bigger picture, we have seen it before in the previous master classes, the electrochemical CO2 reduction technology. Most of the work in this field has been done on the left bottom side of the arrow on lab scale, and a bit on flow cells. But in order to proceed to the industrialization or commercialization of this technology, there is still a lot to be done. And in this project, we aim to work towards a demonstration or a pilot plant where we will focus on actually the middle part, so the system integration and the pilot development. We all know the bottlenecks of CO2 reduction and the pure CO2 solubilities in the half cells or the H cells, low current densities, and upscaling stability issues. For that, we will use gas diffusion electrodes in this project. So going to the next slide. As I mentioned, we work on the design of gas diffusion electrodes and the electrocatalyst integration. As already showed before by Toni, the gas diffusion electrodes, you have a gas diffusion layer, a hydrophobic layer, the gas side and the liquid side, and your catalyst is somehow integrated on that gas diffusion layer. What we do in this project is we try to study the composition of this gas diffusion layer together with the catalyst layer, trying to optimize the morphology and to upscale to larger electrodes. Next. So some key achievements and results. First, on the gas diffusion layer itself. So without any catalyst, we make some gas diffusion layers ourselves. We tested them, characterized them, and then mainly the water permeability, the pore size, the mechanical robustness. We compared with commercial gas diffusion layers, and compared to those, we had quite better performance, I would say, in the sense of lower water permeability and smaller pore sizes. Of course, that's not everything, because this is still without any catalyst. So when we integrate a catalyst, there are, of course, several possibilities. I will not go into details here, but we worked on a thin electrocatalyst, and that's because the focus in this project is to work towards formate. And we developed a methodology to increase the amount of thin active sites and incorporate it in a homogeneous way in the gas diffusion layer, which realized relatively high current densities, around 250 and 500 milliamps per square centimeter, and also reasonable Faraday efficiency, 60 to 80%. Currently, we are working on other electrocatalysts. And if you go to the next slide, the potential for impact, what we will do in the near future is looking towards making these electrodes larger. In the graph, you can see in red a 10 squared centimeter electrode, which is the typical size of the experiments we are doing. Then next to that, you see a 300 squared centimeter electrode, which is a bench scale setup, which will be used and is being used in this project. On the right, you see even a much larger segmented gas diffusion electrode, which will not be used in this project, but at least it's just to show that larger areas are possible. In this project, we will look into the possibility of stacking the different electrodes, and we will collaborate with the University of Antwerp, where they make the electrocatalysts, and we integrate them in the gas diffusion electrodes. So, and the most important impact from this project is the demonstration of the direct CO2 reduction technology. Next. Yeah, our team. So we have a team of technicians, researchers, and our program manager. In the right, you can see some of the facilities which are heavily used when making our gas diffusion electrodes. Then the takeaways in the next slide. So electrocatalysts may behave differently when integrated with electrodes. We all investigate the electrocatalyst in typically in H-cell smaller scales, but when proceeding to larger surfaces, catalyst integration brings along different factors. So there is not one fits all procedure to design your gas diffusion electrode. There are a lot of different factors playing a role: ink composition, the morphology of the electrode thickness, the binder type, pore size, etc. Last one, we have developed a novel way of GDE fabrication, which ensures a high amount of active sites and current density. Thank you. Yeah, in the next session, we have two breakout sessions. One of them is about the catalysts and electrodes for electrochemical CO2 conversion, where we will discuss in more details all these aspects. Thank you.
Thank you very much. I'll invite Elena from TNO.
They must have made a mistake. They're still saying that they miss a palette.
Hi, can you hear me?
Yes, we hear you. Thank you.
All right. So, hi, my name is Elena Perez, and I work as an electrochemical scientist at the Dutch Research Institute, TNO. So, I would like to start with a question. Next slide, please. So, have you ever wanted to apply your new technological developments in the industry? So, well, this at TNO, we are working to make this happen. So specifically for this project, we are working on how to increase the technology readiness level of the direct electrochemical conversion of CO2 to formic acid, and how to make it relevant for the industry. So in the next slide, please. In the ambit or in the context of the electrochemical CO2 conversion studies, many of these studies are focused on material development, like the other speakers already mentioned, how to get the most efficient catalyst, the most efficient material, or what is the best support for the catalyst nanoparticles, or what is the best electrolyte composition, amongst others. And material development, although it's essential, it is only one side of the coin. So when a technology is scaled up, a new set of challenges arise. And here in the scale-up process is where TNO where we put all our efforts. And we try to solve these scale-up challenges with engineering solutions. So for instance, one of the things we are focused on is the electrochemical reactor design. And here we do it from three different fronts. So the first one is how to improve the fluid dynamics of the system. So we have designed and manufactured different types of flow channels that you can see there in the right images. And we have demonstrated that with such flow fields, we can double the performance of the reaction in terms of current densities and efficiencies. So we also work on increasing the active surface area of the electrodes without paying the price of needing to have bigger reactors. So for instance, we use these 3D types of electrodes. And we are also looking into different solutions on how to directly separate the product form from the reaction stream. So for instance, in this project, we are using this 3-compartment electrolyzer where the formic acid form is separated in situ inside the reactor. And besides the reactor development, next slide, please. We are also actively looking into the entire value chain. So from the upstream to the downstream processes. So yeah, we ask ourselves questions like, how can we integrate the CO2 capture with the CO2 utilization in one single process? How can we integrate the separation and the purification of the product in the system, as I was mentioning with this 3-compartment system? but also questions like what are the needs of the industry, or what is the target electrochemical product going to be used. So for our research, we try to adopt a process integration approach where we consider the interaction between different units, and we try to optimize the whole system rather than optimizing them separately. So for this project, we are currently developing a pilot demonstrator, which will help us our quest to find the ultimate CO2 conversion process and bring it closer to its real implementation in the industry. And yeah, for all these questions and requests that we always have a common denominator, and it is how can we make this entire process economically more attractive. So if you want to know more about these topics and discuss, you can join us in the last breakout session at 16:20 on advantages of novel electrolytes and reactor designs for electrochemical CO2 conversions.
Great, thank you very much, Elena. Good, so that brings us to the second coffee break. I invite you again to join the different rooms. And again, if you would like to discuss more with Toni, then he will be in the coffee break room under the meets and virtual meets. And you'll see the coffee break with Toni. So I invite you to join that, grab a coffee, and we'll see you in the breakouts. Let's go ahead and keep things on time. So at 3:45, we'll go ahead and start the breakout sessions again. Thank you, everyone.